Hello everyone and welcome to this video. Today I'm going to be talking about KSSM Mathematics Form 4, Chapter 5, Network and Graph Theory, specifically the subtopic Identify and Draw Subgraph and Trees. The learning objective of this video is to identify and draw subgraph and trees. So hopefully after watching this video everyone will be able to identify and draw subgraph and trees. The first topic of the video will be on subgraph. So what is a subgraph? A subgraph is a part of a graph or the whole graph redrawn without changing the original positions of the vertices and edges. Well, as we can see here, this is a graph, and if you were to draw a subgraph of it, you can draw it like this, like this, like this, or any one of these examples here. We can call this a subgraph because it did not change the original position of the vertices and edges of the original graph. Okay, secondly, if a graph A is part of a graph B, then the graph A is a subgraph of graph B. It can be written out as A subset B. Okay, so let's call this subgraph a graph A and call the original graph graph B. So according to this, since it is part of a graph B, we can call this A subset B. A graph H is said to be a subgraph of G if the vertex set of graph H is a subset of the vertex set of graph G. The edge set of graph H is a subset of the edge set of graph G. And the vertex pairs of the edges of graph H are the same as the edges of graph G. So this might be a bit hard to understand, but basically what it means is a vertex in graph G is a subgraph of graph G. So let's call this graph G, and we take a random vertex. Let's take vertex Q. So over here, see it as vertex Q. Vertex Q can be considered a subgraph of graph G. Next, an edge in graph G along the vertices it connects is a subgraph of graph G. And lastly, each graph is a subgraph of itself. Next, identifying subgraphs. So we are going to do a few examples from the textbook. Determine whether diagram 1, 2, 3 and 4 are subgraphs of graph G. We'll start with diagram 1 and 2 first. Okay, so diagram 1 is a subgraph of graph G because the vertex pair for HE5 is the same. So if we look clearly here, the vertex pair for HE5 is P and S, and when they draw back the subgraph, it is still P and S. So it is correct. Next, diagram 2. This is not a subgraph because the position of E2 is not on vertex Q. E2 is a loop over here, but on the original graph G, E2 is actually at vertex Q. So this is wrong. Now moving on to diagram 3. This is not a subgraph of graph G because the edge connecting vertex P and vertex S is not E3. Since a subgraph must be the same as the original graph, the label must be the same also. So E3 should have been E5 because if you see here, the edge connecting vertex P and S is actually E5 and not E3. Diagram 4. Diagram 4 is also not a subgraph of graph G because the loop and the edge connecting vertex Q and vertex R are wrong. If you can see clearly here, E3, E2, E3 and E2, they are swapped out, and this is supposed to be E2 and this is supposed to be E3. So no, this is not a subgraph of graph G. Okay, so now we'll be talking about trees. A tree of a subgraph is a subgraph of the graph with the following properties. A simple graph without loops and multiple edges. All the vertices are connected and each pair of vertices is connected only by one edge. And C, the number of edges is equivalent to the number of vertices minus 1. Let's say the number of vertices is n, so the number of edges would be n minus 1. Okay, here are two examples of trees. So if we look back at the properties, a simple graph without loops and multiple edges, yes, that is correct. All the vertices are connected and each pair of vertices is connected but only by one edge. Yep, correct. All the vertices are connected and each pair of vertices is connected by only one edge. So, and lastly, the number of edges is equivalent to the number of vertices minus 1. Let's try to check that. The number of edges here is 1, 2, 3. So 3 equals the number of vertices is 1, 2, 3, 4. 4 minus 1. So 3 is equals to 3, so yes, this is a tree. Okay, so why did we have to learn the tree properties of a tree just now? We learned it to identify trees and to draw trees further later in the topic. So here, let's try to identify trees first. Diagram 1, we have to identify whether these two diagrams are a tree or not. So first one, diagram 1, a simple graph without loops and multiple edges. Yes, this is correct. And secondly, all the vertices are connected and each pair of vertices is connected only by one edge. Yep, all the vertices are connected and each pair of vertices is connected only by one edge. And lastly, the number of edges is equivalent to the number of vertices minus 1. And the number of vertices here is 1, 2, 3, 4, 5. And the number of edges is 1, 2, 3, 4. So 4 equals to 5 minus 1. 4 equals to 4. Yes, this is correct. So this diagram is a tree. Now we move on to diagram 2, a simple graph without loops and multiple edges. Yes, this is correct. However, for the second one, all the vertices are connected. Even though this is true, all the vertices are connected here. But the other requirement is each pair of vertices is connected only by one edge. However, this is not a tree because vertex B and vertex E can be connected in two ways, BE and BCDE. BE or BCDE. So since there are multiple ways to connect vertex B and vertex E, this is wrong. It is not connected only by one edge. And lastly, we check the number of edges is equivalent to the number of vertices minus 1. Number of edges here is 1, 2, 3, 4, 5. And the number of vertices is 1, 2, 3, 4, 5 as well. And 5 is not equals to 4, so this is wrong. So we can conclude that diagram 2 is not a tree because it does not fulfill the requirement of being a tree. Now the second one, more examples on identifying trees. So determine whether each of the following graph is a tree. Now we'll try to go a bit faster on this one since I've explained in detail on how to identify trees. So A is not a tree because it has 6 vertices and 7 edges. It does not fulfill the requirement that number of edges is equivalent to the number of vertices minus 1. And each pair of vertices can be connected in various ways. So yes, this is not a tree. Now for B is a tree. It has 6 vertices and 5 edges, and each pair of vertices is connected only by one edge. So this is a tree, correct? Now we move on to diagram C and diagram D. Diagram C is a tree. It has 6 vertices and 5 edges. Each pair of vertices is connected by one edge. However, for diagram D, it is not a tree because it has 6 vertices and 4 edges. Once again, it does not fulfill the requirement of number of edges is equivalent to the number of vertices minus 1, and vertex R and vertex T are not connected to the other vertices. It is just left alone over here, so this is not a tree. Okay, so now we'll be going to drawing trees. We have to draw 2 trees for the following information given. So A, 6 vertices. Since they ask us to draw a tree with 6 vertices, in our mind we would automatically know that the number of edges would be 5. So 5 edges, just write that down so that we don't forget. 5 edges. So here is the textbook answer for it. It has 1, 2, 3, 4, 5 edges and 1, 2, 3, 4, 5, 6. Well, this is correct. So let's try to draw another tree on our own. Just have to put down the vertices first. 1, 2, 3, 4, 5, 6. Now we connect them together with lines. This. Yeah, I would call this a tree because it fulfills all the requirements and it does not connect in more than one way. Now for the second one, it wants us to draw a tree with 8 vertices. So once again, we would know that if it asks us to draw with 8 vertices, it would have 7 edges. If you look at the example here, it has 1, 2, 3, 4, 5, 6, 7, 8 vertices and 1, 2, 3, 4, 5, 6, 7 edges. Now let's try to draw one on our own. Basically, when drawing trees, I try to keep it as simple as possible so that we don't mess up. Because drawing trees could be a little bit complicated sometimes. 1, 2, 3, 4, 5, 6, 7, 8. I prefer to go in zigzag kind of shape, so it's easier to draw it out. 5, 6, 7. So once again, we fulfill the requirements of a tree. It has 8 vertices and 7 edges. Okay, now we move on to the last two examples. Now they switch it up a little. Instead of giving us the number of vertices, they give us the number of edges now, but still the same. Since it has 4 edges, we would know that it needs 5 vertices. So here is an example from the textbook. It has 1, 2, 3, 4, 5 vertices and 4 edges. Yes, this is a tree. Now I'll try to draw mine, which is 1, 2, 3, 4, 5 vertices, and then the edges. So now it fulfills the requirements of being a tree. 5 vertices, 4 edges. None of them are connected in 2 ways, in more than 1 way. So yes, that is a tree. And now moving on to the last example, 9 edges. So since it has 9 edges, we would know the number of vertices would be 10 vertices. Here's a great example of how to draw a tree with 9 edges. Now we try to create one on our own. I'm just gonna do the same thing again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. Now just have to draw the 9 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this is a tree, and I would say it fulfills the requirements of a tree, and 9 edges, 10 vertices. Now we move on to a bit harder one, drawing trees based on graph. Well, it's not actually very hard. All we need to know is that the position of the vertices must be the same as the original graph given. So let's try to draw one now. Since it has 5 vertices, we would know the tree needs 4 edges only. First, we can draw one like this. We must remember that the vertices and lines must match the original graph. Draw one like this. I will consider this a tree of this graph here. And another example will be maybe like this. Draw back the 5 vertices at the same position. Draw it like this as well. Basically, we just have to make sure that the vertices and the edges are at the same position. We just have to remove a few of them to make sure they fulfill the requirements of a tree. Okay, so now we're done with this. Let's go on to the next example. This one has 1, 2, 3, 4, 5, 6 vertices. So the number of edges should automatically be 5 only. Let's just write that down first. 6 vertices. 1, 2, 3, 4, 5, 6. And the number of edges should be 5 edges for a tree. Once again, just draw back at the same position. 1, 2, 3, 4, 5, and 6. Just draw the lines. Draw 5 edges only. So I think I would draw it like, oops, sorry, just have to change the color. I'll draw it like this. And another way I would draw it would be like this. Just have to draw back at the same position. It might be a bit smaller, but it's okay. Just have to make all the vertices are connected by only one edge. So yeah, that's basically it. Okay, now we move on to another problem. The following diagram shows an undirected weighted graph. So we have to draw a tree with a minimum total weight. So the first step would be to find out the how many edges needs to be removed. So if we count here, there are 1, 2, 3, 4, 5, 6, 7 edges, and 1, 2, 3, 4, 5 vertices. Since it has 5 vertices, if we were to draw a tree, we can only have 4 edges with 5 vertices. So since it has 7 edges right now, we need to remove 3. And if we need a minimum total weight, we'll have to remove the edges with the greatest weights. So in this case, the greatest weights would be firstly 25, 20, and 19. So that would be PQ, QR, and PT. Once you remove the edges with the greatest weights, the graph would look like this. But this graph is not a tree yet, because vertex P over here is not connected to any of the other vertices, as one of the requirements of a tree would be all the vertices are connected, and each pair of vertices is connected by only one edge. But since P is alone here, it is not connected to the other vertices. It is not a tree. And tree edges RS, ST, and RT connect 3 vertices. So that is also wrong. Between the weights 19 and 25, keep weight 19 because its weight is smaller. 19 and 25, we are basically choosing one to keep because we need to join vertex P with the other vertexes. And between the weights 12, 14, and 17, we would remove one of them so that it won't connect 3 vertices. So after removing, we will remove weight 17 because it is the greatest weight. So after removing the line RS and add line PT back, the graph will look like this, and the graph obtained here is a tree, as it fulfills the requirement of being a tree. Now the minimum total weight of the tree is 10 plus 12 plus 14 plus 19 equals to 55, and this is the tree with a minimum total weight. Okay, thank you for watching this video. I hope you have learned something. This video was a group effort from me, Ryan Lau, Teh Kah Hao, Jeremy Lu, and Haresh Sundram. All of us are from 4 Jerai. Thank you.